Dear students, this episode consists of the following sub-modules: mapping climatic data, isotherms, isobars, and isoHYETS. Isobars and isotherms. What is an isobar? Isotherms, isobars, ISOHYETS, dew point temperature, isodrosotherm, contouring, temperature contours, pressure and temperature, dew point reports and contours, pressure and dew point, conclusion. Isobars and isotherms. Isobars and isotherms are lines on weather maps which represent patterns of pressure and temperature respectively. They show how temperature and pressure are changing over space and so help describe the large-scale weather patterns across a region in the map. What is an isobar? Isobars are lines of constant or equal pressure on a weather map. They can be used to find areas of low or high pressure over a broad area, and they can tell us how intense the system may be. On weather maps, you may have noticed areas that have a large L or H over a region with lines circling around them. The L stands for low pressure, where we would expect to find the lowest pressure, and H stands for high pressure, where we would expect to find the highest pressure. The lines circling them are isobars. Generally, the lowest pressure is where precipitation is most likely to fall, and high pressures are usually associated with clear and sunny conditions. Where the isobars are close together, windy conditions may be expected. Elongated areas of low pressure on surface and upper air weather maps are called troughs, and elongated areas of high pressure are called ridges.
So, why do we use isotherms and isobars? Isotherms and isobars allow us to view large-scale processes much more easily than looking at the raw data from individual weather stations itself. For example, Figure C is temperature data across the US. Figure D is of the same data, but this time colors and isotherms have been added. Just by glancing, it is much easier to see where the warmest and coldest temperatures will be across the US, and it gives you an idea of what to expect in certain regions.
Isotherms. A line connecting points of equal temperature is called an isotherm. That means at every point along a given isotherm, the values of temperature are the same. Isotherms are represented by dashed orange contours in the weather map. The black numbers are station reports of surface temperature in degrees Fahrenheit, which is the unit for temperature in the US. Most other nations of the world use Celsius. The isotherms displayed were generated from the observed values of temperature and have been plotted at intervals of 5 degrees Fahrenheit. The small orange numbers are contour labels which identify the value of an isotherm, 75 and 85 degrees Fahrenheit. For example, reported temperature values in Nebraska, southern Iowa, and Illinois are generally 90 or above and are therefore located south of the 90 degrees contour. This surface temperature information has been incorporated into a more complex surface map generated for the same time. Reported temperatures show that a dome of very high air has pushed its way into Nebraska, where temperatures are above 90. More pleasant weather is found across North Dakota and Minnesota, where temperatures are in the 70s. The word originates from Greek, where isos means equal and therm means heat. Isotherms are created from regular scheduled simultaneous temperature readings at different locations. For a proper comparison between the observation places, the measured temperature values are corrected for each location as if it was located at sea level. Isotherms help to visualize and interpret the horizontal temperature distribution of an area by showing patterns of temperature on a weather or oceanography map. Constructing a map of isotherms is an elementary step in temperature data analysis, and the process in general is called contouring. It can also be done for other parameters such as barometric pressure, that is isobars, geopotential height, that is ISOHYETS, dew point temperature, isodrosotherms, wind speed, which is also known as isotax, and salinity, which is isohalenes. Isotherms are always smooth, labeled with the values, and mostly parallel to each other. Although the interval between the isotherms is arbitrarily chosen within the same map, it is a constant and usually a round value. The value is selected such that the contour map both contains enough contours to show the patterns, and yet it is not crowded with too many lines. Because data is available only in the temperature observation points, interpolation should be used to create the isotherms between the measurement points. On the other hand, extrapolation to areas where no data is available is not acceptable. An isotherm should never split, cross, or touch another isotherm, because then at the crossing point it would have two different temperature values, which is physically impossible. Sometimes contour maps are enhanced using color fillings when the area between pairs of isotherms is filled with special colors, so a particular color denotes the range of values between the two temperature zones. The relative spacing of the isotherms indicates the temperature gradient, the amount by which the temperature values vary across each unit of horizontal distance in a direction perpendicular to the isotherms. The gradient is larger where the isotherms are closer. From the contour maps, areas of large gradient as well as flat fields can be easily identified. In general, contour lines join areas of equal value of the variable that is being measured and are also known as isophytes. The distance between the contour lines depict the rate of change in that third variable. If the distance between the lines is close, the rate of change is larger over a small distance. These lines are also known as isophytes. There are a variety of specialized Isoplet maps. Examples include bathymetric, that is, showing sea floor elevation, ISOHYETS, showing rainfall, isopax, which show rock or sediment, isotax, showing wind speed, and isobars that show air pressure.
Isobars. A line connecting points of equal pressure is called an isobar. That means that at every point along a given isobar, the values of pressure are the same. Isobars are lines of equal atmospheric pressure that are used in meteorological maps. An isobar map shows the horizontal change in pressure or the pressure gradient that occurs due to the movement of air over large spaces. The isobar map above shows closed isobars around a low pressure system. The black numbers are station reports of sea level pressure in millibars. Isobars are normally drawn at 4 MB intervals with 1000 MB being the base value. The small blue numbers are contour labels which identify the value of an isobar. ISOHYETS. It is a line drawn through geographical points recording equal amounts of precipitation during a specific period. The isohyetal method is used to estimate the mean precipitation across an area by drawing lines of equal precipitation. The method uses topographic and other data to yield reliable estimates. Isohyets are contours of equal precipitation analogous to contoured lines on a topographic map. In the isohyetal method, precipitation values are plotted at their respective stations on a suitable base map, and isohyets are drawn to create an isohyetal map. Isohyetal lines are based on interpolation between rain gauge stations. While constructing isohyets, it is assumed that rainfall between two stations varies linearly unless abrupt changes in topography indicate otherwise. Isohyet maps are maps drawn with contour lines that measure rainfall. Isohyet maps are similar to isobar maps and isotach maps. The map also has colors to help display the different levels of rainfall in the area for those who can't read a contour map. Isotachs. An isotach map is one that consists of contour lines displaying equal wind speeds. The isotach map shows a jet streak that extends from Kansas into the Great Lakes. The wind speeds and directions are also visible. Isopleth Maps. Isopleth maps generalize and simplify data that has a continuous distribution. Unlike choropleth maps, the data is not confined to a predefined unit such as a country. These maps are great for showing gradual change, since there are no set boundary lines that will cause an abrupt change. The data is shown by series of lines called isopleths that connect points of equal value. It is important to note that isopleths always form enclosed circles as well. The isopleth map below displays the distribution of rainfall. As precipitation is a gradual occurrence, an isopleth map was appropriate.
Dew point temperature. Dew points indicate the amount of moisture in the air. The higher the dew points, the higher the moisture content of the air at a given temperature. Dew point temperature is defined as the temperature to which the air would have to cool at constant pressure and constant water vapor content in order to reach saturation. A state of saturation exists when the air is holding the maximum amount of water vapor possible at the existing temperature and pressure. Isodrosotherm. A line connecting points of equal dew point temperature is called an isodrosotherm. That means at every point along a given isodrosotherm, the values of dew point temperature are the same. Isodrosotherms are represented by dashed green contours. An image of reported dew point temperatures and isodrosotherms has been given below. The black numbers are station reports of surface dew point temperature in degrees Fahrenheit. The isodrosotherms were generated from the observed values of dew point temperature and have been plotted at intervals of 5 degrees Fahrenheit. The small green numbers are contour labels which identify the value of an isodrosotherm, 55, 65 degrees Fahrenheit. In the image below, this surface dew point temperature information has been incorporated into a more complex surface map generated for the same time. Reported dew points show that a dome of very moist air has pushed its way into Iowa, Illinois, and southern Michigan, where dew point temperatures are above 70. Such high dew points usually mean humid and sticky weather conditions. On the other hand, pleasant weather is found across North Dakota and Minnesota, where dew points are in the 50s and the air is much drier. Contouring. Contour lines are the means of relating the vertical dimension, which is the third dimension of the topography of an area, to the two-dimensional surface of a topographic map. Contour lines should be visualized as the intersection of the land surface with a series of equally spaced horizontal planes that pass through the surface. The vertical distance separating these planes is termed the contour interval, CI. Contour intervals are determined by the map scale and the amount of topographic variation within the map area. As viewed on a topographic map, the spacing of contour lines, but not the contour interval, varies according to the changes in slope angle of topographic features. Because of this relationship, a few simple rules of contour lines will prove helpful in interpreting the vertical dimension of topographic maps.
Topographic map contour lines. Contour lines are the greatest distinguishing feature of a topographic map. Contour lines are lines drawn on a map connecting points of equal elevation, meaning if you physically followed a contour line, elevation would remain constant. Contour lines show elevation and the shape of the terrain. They are useful because they illustrate the shape of the land surface, its topography on the map. In order to keep things simple, topographic maps show lines for certain elevations only. These lines are evenly spaced apart. We call this spacing the contour interval. For example, if your map uses a 10-foot contour interval, you will see contour lines for every 10 feet of elevation, lines at 0, 10, 20, 30, 40 and so on. Different maps use different intervals depending on the topography. If, for example, the general terrain is quite elevated, the map might run at 80 to even 100 feet intervals. This makes it easier to read the map. Too many contour lines would be difficult to work with. Look in the margin of your map to find out its contour interval. To make topographic maps easier to read, every fifth contour line is an index contour. Because it's impractical to mark the elevation of every contour line on the map, the index contour lines are the only ones labeled. The index contours are a darker or wider brown line in comparison to the regular contour lines. You'll see the elevations marked on the index contour lines only. To determine elevations, pay attention to the amount of space in between lines. If the contours are close together, you're looking at a steep slope. If the contours have wide spaces in between, the terrain is relatively flat.
Temperature contours. Reference weather map, current weather map. This surface meteorological chart shows the temperature pattern over the continental United States and is updated every hour. Surface temperature reported at each station are contoured every 5 degrees Fahrenheit. Areas of warm and hot temperatures are depicted by orange and red colors, and cold temperatures below freezing are shaded blue and purple. In the example above on the left, there is a large change in temperature from western Oklahoma to central Texas. This suggests that a front is somewhere in the area. You can check the current map to see if there are areas that also appear to be affected by fronts. Pressure and temperature. This panel depicts temperature and sea level pressure contours. This chart is useful for finding fronts and high and low pressure systems. The solid black contours represent pressure contours or isobars in millibars. The isobars have a contour interval of 4 millibars. The wind speed is directly related to the distance between the isobars. The closer the isobars are together, the stronger the pressure gradient and the stronger the wind. The colored regions represent the surface temperature. The contour interval of the isotherms is 5 degrees Fahrenheit. From the chart above, you can sometimes find warm and cold fronts. Fronts are usually located where temperature changes drastically over a short distance. Dew point reports and contours. This surface meteorological chart shows the dew point temperature pattern over continental United States and is updated every hour. Dew point temperature is a measure of moisture in the air and is contoured here every 5 degrees. In the example above on the left, there is a large change in dew point temperature from New Mexico to central Texas. This suggests that a dry line is somewhere in the area. You can check the current map, which is to the right, to see if there are areas that also appear to be affected by dry lines. Pressure and dew point. This panel depicts sea level pressure and dew point temperature. This chart is useful for finding fronts and high and low pressure systems. The solid black contours represent pressure contours or isobars in millibars. The isobars have a contour interval of 4 millibars. The wind speed is directly related to the distance between the isobars. The closer the isobars, the stronger the pressure gradient and the stronger the wind. The dashed color-filled regions represent areas of equal dew point or isodrosotherms. The contour interval of the dew point contours is 5 degrees Fahrenheit. From the map above, you can sometimes find warm fronts, cold fronts, and dryness. Fronts are usually located where the dew point changes drastically over a short distance. Conclusion. The distribution of various elements of climate and their analysis is often done by climatological maps. The global distributions of temperature, pressure, air mass, etc. are shown by such maps. Similarly, many of the critical values obtained during analysis of weather charts when superimposed on any base of relevant distribution maps makes analysis more significant. Many of such maps use Isopleth mapping techniques, and lines of the same value separates the zones of specific ranges. Contours are lines that connect locations of equal value that represents continuous phenomena such as elevation, temperature, precipitation, pollution, or atmospheric pressure. The line features connect cells of a constant value in the input. Contour lines are often generally referred to as isolines, but can also have specific terms depending on what is being measured. Some examples are isobars for pressure, isotherms for temperature, and isophytes for precipitation. The distribution of the contour lines shows how values change across a surface. Where there is little change in a value, the lines are spaced farther apart. Where the values rise or fall rapidly, the lines are closer together. Thank you.